It's already set up for like left-handed from this side, so I'm not gonna turn around. There's a way to do it, but I'm not gonna bother. Yeah, I get what you're saying. Because of the cables going to it, we can't like turn the thing around. But that's a good point. So let's go ahead and get started. So as you guys know, this test is gonna be on chapters 15, 16, and then part of 17. I believe she covered the first 2 sections of 17, right? Yeah, we'll go with that. Up until impulse momentum. So you'll notice on my review, whenever we get to chapter 17, I do have equations for the other content from chapter 17. Just ignore those equations. I didn't edit them out. The problems on here, though, those are related to what your test is going to cover. So hopefully we can get through all of these, but again, I do post the solutions afterwards, and they are very nice and neat. So I'll try to, if there's ever a time where you don't understand like my handwriting or something, just let me know and I'll clarify. So let's begin with this thing. Can everyone see that okay? Yeah? Unless I'm like blocking you. Okay. So I believe this one was a homework problem, but this is still a really good one to do. It says, a load is to be raised 20 feet by the hoisting system shown, assuming gear A is initially at rest and it accelerates uniformly to a speed of 120 RPM in 5 seconds, and then maintains a constant speed of 120 RPM. Find the number of revolutions by gear A in raising the load and the time required to raise the load. So what I always like to do is start off with my knowns and unknowns. So step 1. So we're told that it has to raise it 20 feet. So I'm going to say that H is equal to 20 feet. We know that gear A initially is at rest. So I can say omega A naught is equal to 0. It accelerates uniformly to a speed of 120 RPM. So I know that WA final, or WA, is going to equal 120 RPM. And we already know that we're probably going to have to convert this, right? So how do I convert RPM? What do I want to convert it to? Radians per second. Good. How do I do that? Very good. 2 pi over 60. Hopefully you all remember that, because I believe that would be the kind of like conversion factor that she wouldn't give on like a formula sheet. I think you just need to know it. So this should give you 4 pi radians per second. We're also told that, so it says it accelerates uniformly to that speed in 5 seconds. So we know that the time is 5 seconds, just for that initial part. So I like to break this problem into kind of 2 different things that are happening. So the first thing that's happening is where it's starting at rest and then it's accelerating. So we have like a constant acceleration. And that component lasts 5 seconds. And then after that happens, then it says it maintains a constant speed of 120 RPM. So once it reaches 120 RPM, it doesn't accelerate any further and it just has a constant velocity. Is everyone okay with that? All right. So we could say after 5 seconds, omega A is constant. And so if I were to tell you that you have a constant angular velocity, what does that mean for alpha? Yeah. Very good. So we need to find theta A, so the number of revolutions of A, and the time to raise the load. So where should we start with this? Good, so we can use that. So that's also called the arc length. So if you guys weren't aware, I'm just going to draw a little picture off to the side. So this is like a side note. So let's say we have these 2 gears. They look kind of like what we have there. So A and B. And we're going to say that these 2 gears, there's no slippage going on. So what does that mean about the velocity at their contact point? Good, so it's going to be the same. So I'm just going to assume that that is that v. So the velocity at the contact point's the same. And so we can say that since the velocity at that point is the same, the total distance as they're rotating would also be the same, right? So the total arc length is going to be the same. So A has a much smaller radius, though. So its revolutions are going to be a lot higher than B. But the total, like, distance traveled, the total circumference is going to be the same between the two. Okay? So I can say, let's see, do you guys know what the equation is for arc length? Very good. S is equal to R theta. So I can say that RB theta B is equal to RA theta A. So we also have some other equations that we can use. So that was like a side note. So I always do knowns and unknowns, and then after that, I write out some helpful equations. So we just said that we have the arc length equation. What are some other ones that we may need to use for this? So we're told for the first part of the problem that A is going to start from 0 and accelerate uniformly to 120 RPM in 5 seconds. Is there any information from that that I'm missing? You guys can shout it out. Good, the acceleration. So we need to find some way to get that alpha that's causing it to accelerate. And so it's constant acceleration, right? Do you guys remember the equation for constant angular motion? Very good. And then we have one more that'll probably be useful for us. I'll write it down. Theta equals theta naught plus W naught T plus 1/2 alpha T squared. So those will probably be helpful. So now we can just start solving. So step 3, solve. So I figure if we think about the arc length, and we know that it has to raise it 20 feet, how do I relate the arc length equation to the height that it has to raise it? Good. What about delta YB? So delta YB equals what? You want me to help you out?
It has to be a derivative.
So you're remembering what we did in the session where we derived the equation. So we just kind of jumped in and put the equation here. So basically what I'm saying is we know that this height here, so this is the h that I want. We want this to go up by h. That means that b, can you guys see that okay? This is going to be h. The circumference will be h. So this s that we had written here, that's the h, or the height that we want to raise it. So we can go ahead and find the number of revolutions that b has to go through. So we can say that theta b, so this is from our arc length equation. So theta b is equal to h divided by rb. So that would be, I'm going to convert the 20 feet into inches. So 20 feet is 240 inches. So 240 divided by the radius of B, which is it 18 or 15? 18. Not quite. 15 goes out, so 18 goes to the end of the teeth. 15 goes to like the edge of the disc where it's in contact with the load. So we're going to use 15 for this one. And so that gives us 16 radians. Then we can use our relation equation that we wrote. So we can say that RB theta B is equal to RA theta A. And so from this, we can say that theta A is going to equal RB over RA theta B. And then plugging in, we have, so which RB am I going to use here? 18, good. So we want to use the radius that's in contact with A. So we have 18 divided by 3 times 16 radians, and that gives us 96 radians. And so generally, well, for this one they're asking for revolutions, so how would I convert radians to revolutions? Very good. So we can divide, I'll put this in red. If we divide by 2 pi, then we end up getting theta A is 15.27 revolutions. And so that's the total number of revolutions that A has to go through to raise the load. So then for the next part of the question, we have to find the total time it takes to raise the load. We already know it takes 5 seconds for the constant acceleration part. So whatever we end up getting, we have to figure out the time it takes for it to raise it for the constant velocity or angular velocity part. So this was for part A, now for part B. So we're going to use the constant acceleration equation. So we can say omega A is equal to omega A naught plus alpha t. So this is to get that alpha. So we get alpha is equal to omega A minus omega A naught divided by t. So that's 4 pi minus 0 divided by 5, which is 4 over 5 pi radians per second squared. So basically what I'm going to try to do is, we know how long, so if I call the constant acceleration part like situation 1, we know that situation 1 takes 5 seconds. We don't know how far it travels though in situation 1. So we know its velocities, we know its acceleration now, we know the time, but we have to figure out just how far it goes. That way we can figure out for situation 2. So we're going to use the other constant acceleration equation. So we have that theta A is equal to theta A naught plus omega naught t plus 1/2 alpha t squared. So theta A naught, I'm going to say is equal to 0. Omega naught is also equal to 0. So remember, we're talking about situation 1. So theta A is going to equal 1/2 times alpha, which is 4 over 5 pi, times the time squared. And that gives us 10 pi. So we know that it takes a total, or that A travels a total distance of 96 radians, right? But we just found out that for situation 1, it goes 10 pi radians. So we need to figure out how it moves in situation 2. So what we can do now is use the same equation. So I'm going to label this as situation 1. Now we have situation 2. So for situation 2, we're going to use the same equation, So we have theta A is equal to theta A naught plus omega naught t plus 1/2 alpha t squared. But as we said before, for situation 2, it's moving with a constant angular velocity. So that means that alpha is 0. And now we can just plug everything in to find the time. So we know that the final distance that it will go is 96 radians. I'll use my blue pen for this. So we have 96 radians. The initial distance, we're going to use the distance that we had found here. So we have 10 pi. And we're going to set this, oops, sorry, that should be a plus. So plus the omega that we have is our constant velocity one, which is 4 pi. And then we have times time. So if you solve this, you should get t is equal to 5.139 seconds. So we know that situation 1 takes 5 seconds, situation 2 takes 5.139. So the total time is going to be 5 plus 5.139 seconds. So t total is 10.14 seconds. Any questions about this one?
How did you obtain theta A again?
Which one?
Before the initial.
For this one? So what we did was we saw from the initial problem that the load is in contact with B. So what we found first was theta B, because we said that the height that the load goes up is going to equal the circumference or the arc length on theta B. So we can find what theta B is, and once we know theta B, we know that we have this relation here, RB theta B equals RA theta A, and we get theta A from that. The big thing with this, I think, is to notice that when we found the theta B, we used 15, but then when we were relating it to theta A, we used 18. So be very careful with which radius you're looking at. The best rule of thumb, or the best recommendation that I have, is use the radius for where it's in contact with whichever part you're looking at. So if you're looking at the load is in contact at 15 inches. If you're looking at A, then the radius is 18 inches. Good? Any other questions about this one?
What's the final answer in seconds?
10.14 seconds. So ready to move on to the next one? Yeah. If you solve this out, yeah. So that would be 25 divided by 5. So it's 5 times 2, so 10 times pi. All right, let's move on to the next craziness. So chapter 15 is an insanely long chapter. There's a lot of concepts in it. So there's, I believe half of my review is chapter 15, just all the different types of questions you could see. So this one looks horrible, doesn't it? It's actually not that bad. This one you can do in like less than 5 minutes.
See it?
All right, we got this. So it says, the disk A is released from rest and rolls down the incline. Knowing that the speed of A is 1.2 meters per second when theta is 0, find or determine at that instant the angular velocity of the rod and the velocity of B. And then it says only portions of the two tracks are shown. So step 1, knowns, unknowns. We're not told too much. So we know that VA at the instant we're looking at is 1.2 meters per second. The angle is 0 degrees. And we have to find the angular velocity of the rod, so I'm going to call that omega AB, and we have to find the velocity of B. But it's at that instant. So what I recommend, draw a free body diagram, because on this, they show this at an angle, but then they tell you that theta is 0. So might as well just redraw it and figure out what it actually looks like. I'm going to knock this over. So step 2, free body diagram. So when theta is 0, I'm going to have the piston B, and then it's going to go like this. And attach to the center of A. And so B is constrained to move only in the x direction, right? And then A keeps contact with that. That should be at the center, just saying. So this is going down this. That's a very steep 30 degrees, but that's our incline. That's more like 60, but I'm an engineer, right? Not an artist. Let's also put the distance on here. So we know that the distance from A to B is 0.6 meters. Okay, so which way, so if A is rolling down the hill, how would I draw that vector? Just down the hill, right? So there's VA. And then if VA is going that way, which way would B be going? Towards A? Good. So I have VB going that way. So how could I solve this? Good. So there we could do conservation of energy. We don't know, though, we don't know the height that A is at initially. So that would make it a little difficult. So we don't really know potential energy. We don't know if there's friction. So that's kind of hard.
How about general motion?
We could do general motion. Or, do you guys remember instantaneous center? That's why I put this problem on here. So instantaneous center is one of the least used tools that you guys have. It's literally she taught it like this. It went by so fast, but it's really helpful. Basically, for this problem, what we could do is we could either break VB and VA into their components. We could try to solve it that way, or we could use instantaneous center and use geometry instead. So for instantaneous center, what we do is we draw lines that are perpendicular to the tail of the velocity vectors. So there's for B. And there's for A. And so where they combine, that is your instantaneous center. And so the instantaneous center is the point on a plane or on a body where you have pure rotation and no translation. So basically, it's kind of like if you were to stand really far off in the distance and look at the two things, they just look like they're kind of doing this. You don't see any sort of it gets the general plane motion equation down from VA equals VB plus omega cross R, and you're literally just looking at omega cross R. But it's all geometric. So we know that, so if I were to redraw this triangle so it's a little more clear, I know that this is a right angle, and I know that this is 0.6 meters. I'm going to call this RAC, so the distance from A to the instantaneous center, and this is RBC. So how am I going to find what this angle is? What do you guys think? But what is that angle? Is it 30 or is it 60? Why do you say 30?
Because
Very good. So you saw it. I'll do a more visual thing. I'm going to ruin my paperclip here because I think this will be a good way to show it. So what I usually tell people in SI is to kind of like take a look at one part of it and like tilt your head and like try to see which way it moves. But what I'm going to do is I'm going to use this paperclip to try and like show it. So we know that A is perpendicular to this line. We know that B is perpendicular to this line, right? So if I put this paperclip right here, and then I rotate it like this by an angle of theta, do you see here that this line is now parallel to that line there? It's not the horizontal. So we basically just rotated both of them by 30 degrees.
I would show that little drawing thing.
You want me to show my drawing? Okay, I'll try that. So another way that I always show it is I'll draw like a general XY axis. So that's kind of like, so if you were to imagine here's point B and here's point A, and then if I were to like basically superimpose the tilted axis on top of it. So what is this angle right here? 30. So this kind of looks like this. So if I were to take and rotate this green one this way, I'm basically going to make like a pinwheel. So they're all going to stay perpendicular, so they're not going to change shapes. So then this is going to go there. This is going to go there. And that's going to go there. Do you guys kind of see it? So wherever you see the red line, that's 30 degrees. 30 degrees. 30 degrees. So I like to look at it kind of like a pinwheel. So if we take and look at this compared to this, then this must be 30. Good? So now this is just a matter of geometry. So we need to get RBC and RAC. So,
Do like the 180 minus 30 minus 90.
hmm?
60 for the top right.
My drawing is horrible for it, but I'm pretty sure it works out to where it's.
I said 180 minus 90 minus 30 to get the 60, so you don't have to do that pinwheel thing.
Right, that works too. Yeah, whatever works for you. I just like to show my little like visual. So RBC, how could I find that? So if I look at tangent, so tangent of theta is going to equal 0.6 over RBC. So RBC is going to equal 0.6 over tangent 30, which gives us 1.039 meters. RAC, something similar. It's going to equal 0.6 divided by sine 30, which is 1.2 meters. And now that we know that, I'm going to say that this is my omega AB, going that way, which makes sense if A is going down the hill, right? So step 3 for this problem, if I have pure rotation, then my equation is just V is equal to omega times R, or R cross omega cross R. But for this one, since it's 2D, we can just do omega times R. So so I know that VA is 1.2, right? So I know VA. So if I write this way, VA equals omega AB times RAC. And then I also have VB is equal to omega AB times RBC. Well, I know VA, I know RAC, so I can find omega AB from that. So omega AB is going to equal 1.2 divided by 1.2. That's weird. And that equals 1 radian per second. Oh, and that's going clockwise. And now that I know omega AB, so I have RBC, I have omega AB now, I can find VB. So VB is equal to 1 radian per second times RBC, which is 1.039 meters, which gives us 1.039 meters per second to the right. That wasn't too bad, right? Yeah.
When do you know that you can use this tool?
So you can use Instantaneous Center pretty much whenever, whenever the geometry is fully known, is what I would recommend. So if you know like more of the distances and stuff, or like if you know the distances and an angle, then you can do it. For some of the ones where like it's just, like you'll see it. For some of them, they're just too crazy. Or like, the reason this one's easier too is that VB is going only in the X direction, so there's no angle involved. And then VA, like we know what it is, we just don't, like, we know the direction, but we don't know the rotation. So like, it just worked out for this one that it's easier. But you can use it in, there's another homework problem where you could have used it to basically show that like you either had like no rotation and only translation, and then for the next part you had all rotation and no, did I say that? The opposite. All rotation, no translation, and then all translation, no rotation. Got it. So like it just kind of helps to kind of visualize, but in this case we could solve the problem. I don't know if she would give you something like this on the test, but I feel like it's really good to like review it. That way you guys have it. Ready to move on? Okay. We're doing good on time. I bet you guys are loving these cranks. There's a whole class on this topic, by the way. So if you really like these things, you can take kinematics and mechanisms, and that's all you're going to do. So just throwing that out there. So this one says, knowing that at the instant shown, crank BC has a constant angular velocity of 45 RPM clockwise, find the acceleration of point A and point D. Okay. So step 1, knowns, unknowns. So we know omega BC is 45 RPM clockwise. How do I convert that again? Good. 2 pi over 60. So that gives us 4.7124 radians per second. And we're told to find acceleration of A and acceleration of D. Where should I begin? What? Yeah, so let's talk about the equations that we have to work with. So what kind of motion does BC have? Pure rotation, good. So if I have pure rotation, so let me write the equations out. So if I have pure rotation, what's my equation for velocity? Omega r, good. What about for acceleration? For the tangential component, right? So the tangential would be r alpha. What about the normal component? Very good. R omega squared. And which direction does it go? Which way does the normal component of acceleration go? It goes towards the center of a circle, right? So it's centripetal acceleration is all it is. So in this case, if B, C were rotating this way, then we know that the velocity at point B is going to go straight up like that. The acceleration, or the tangential acceleration of B, will go up, and then the normal will go inwards. But it says that we have a constant angular velocity of 45. So what does that mean about alpha? Very good. So alpha BC is 0. So that means that my tangential component for B is 0. So we just have the normal component, and then we have the velocity of the point. Now let's talk about the other rod. So what kind of motion do you guys think that one has? You said translation. You said general motion. So why do you say general motion? Let's just write down the equation for it. What's the equation for general motion? Good. So if I were to say, so this is just a general equation. So VB equals VA plus what? VB relative to A. And what does VB relative to A equal? Is it omega cross R, or R omega? Everyone kind of remember that? I see some of those like smiles that go, yeah, I totally got this. And then for acceleration, so I could say AB is equal to AA plus, and then I'm going to have AB relative to A. And what does AB relative to A equal? Alpha R.
Omega squared R.
Good. Everyone okay with this? But why did you say this only has translation? Very good. So this problem actually had a trick to it. So do you guys see at the instance shown that B is moving perfectly straight up? Which way is A constrained to move? It can either go up or down. So let's say it's going up. Do you remember that instantaneous center problem that we just did? If I were to try to draw perpendicular lines to both of these, let's see what happens. So I'll have a line like this, and I'll have a line like this. And they never cross. So since they never cross, what can we say about the problem? Do we have translation, rotation, or general plane motion? Translation, good. So they would cross if it was kind of like rotating. Do you see what I'm saying? But they're literally just like, if you guys can see my pin, like they're literally just moving like this at that instant. So at that instant in time, and like based off the figure, it's like this, it's not rotating, it's just translating. So we can basically ignore the general plane stuff as we only have translation. So where should we start for this problem? Which like arm do I want to look at? Do I want to look at DBA or BC? Good, so always start with the one that you know the most information about. So we're going to find the velocity and acceleration from, so VB, AB, from crank BC. So I'm going to draw, I kind of already drew it up there, but I'll redraw it down here. So we know that VB is going up. And then we know that we have omega BC. And then this R is 4 inches. I'll draw another diagram just for the acceleration. That way it doesn't get too confusing. So how would I find VB? Very good. VB equals omega, or R times omega. So we have 4 inches times 4.7124 radians per second, which gives us 18.85 inches per second going straight up. So there's VB. And then, this is for velocity. Then for acceleration, it's going to look very similar. So we would have, just drawing the general equation again, ABT, ABN, and then instead of that we would have alpha. And then we also would have the omega still. What does alpha equal?
0.
So alpha is 0. And as we saw from our equations up here, if alpha is 0, then the tangential acceleration component is 0. So all I have is the normal component of acceleration. So I can say that AB tangential is equal to 0. AB normal is equal to R omega squared. So we have 4 inches times 4.7124 squared, and that should give you 88.83 inches per second squared, and that's going to the right. Good so far? So we're trying to find the acceleration of point A and the acceleration of point D. So now we need to, since we've pretty much finished everything we can find as far as point B goes, we can move on to the next lever arm. So number 4, we're going to look at velocity and acceleration for rod DBA. So I'm going to draw my little diagrams again. So let's do the velocity one first. So for velocity, I know that VB is equal to 18.85 inches per second. And then we know that VA is going up like that. We said that omega of dBA is equal to 0. So what does that mean VA equals? Very good. So VA equals VB, which is 18.85 inches per second. Well, the velocity was easy. So now let's look at the acceleration. So we know that the acceleration of B is going in the x direction, right? Because the tangential was 0. We know the normal is in the x. So we know that AB is 88.83 inches per second squared. So then we need to find the acceleration of point A and the acceleration of point D. So let's start with point A first. So here's my point A. So I'm going to have two components of acceleration I need to look at, the tangential and then the normal. So the tangential component is going to look like that. And I'm going to call this acceleration of point A relative to B, tangential. Okay? And then for the normal, it's going to go towards point B. I'm going to say this is A relative to B, normal. So we need to figure out what this angle is. So let's come back up to the top here. So from the geometry, I'm going to redraw this little triangle here. This is C, this is B, this is A. So my hypotenuse is 8, this is 4, so what is this angle right here? So theta is going to be sine inverse of 1/2, which is 30 degrees. Okay? So then, if I were to draw a line going up right here, sorry, then do you see that this angle right here is also 30 degrees. So that 30 is this 30. I can't zoom out any farther, otherwise I would. Wait, yeah, I can. So this line that I drew here is the same vertical line that VA is moving up, or it's the same vertical line going from A to C. Good? Okay, so I'll zoom back in a little. Can you guys see that okay? Okay. So if that angle's 30 and we do my little rotation trick, we get that this angle here is also 30. You guys could try the little rotation trick if you want, but I'm going to try to save a little bit of time. So now we can just go ahead and write our equation out. So going back up to what we wrote here, I shouldn't have put an x through this AB relative to A part. I meant to only put it through this part here, right? Because we still have the omega, and we still have an r there. It's just the alpha that's 0. I just...
So AB with respect to A is always directly from A to B.
For the normal.
That's how you found A and B.
Yeah, so the normal, so basically what I'm doing is I'm saying if this is rotating, the normal always goes towards the point that you're looking at, and then tangential is always going like perpendicular to that. So what we can write here is that the acceleration of point A is equal to the acceleration of point B plus A relative to B tangential, and then plus A relative to B normal. And I'll write what these equal here. So A relative to B tangential is going to equal R alpha, I'm just going to call this DA, because this was point D. So that's, or if you want to call it, what did I call it before? DBA. So this could be R alpha DBA. And then the normal component is equal to negative R omega dBA squared. Sorry, so I wrote the wrong one here, but we said from the velocity equation, or from the motion, that the omega is 0. So it's actually this component that's 0. Because we can't say for sure, so ignore what I was saying about this one. This is incorrect. So ignore that. That was my bad. we can't say that alpha dBA is 0 just because the other one wasn't accelerating, right? So we don't know what it is. It may be 0, and we can calculate it, but we have to assume that it's not 0 unless otherwise told. So it's actually our normal component that's 0 because we said that for this rod, the omega is 0. We're okay. So then, solving this out, we should get acceleration of A in the J is equal to 88.83 I. And then for the tangential component, we said it's R times alpha. So that's so we're going to have 8 alpha dBA. And then for the I component, it's going to be cosine of 30 based off of this. And then I have plus sine 30J. And we know that A can only move in the J direction, so that's why I put a J there. So from this equation, we have 2 unknowns, but we have an I and a J direction. So what we'll do is we'll look at both directions. So if I look at I, so I'm going to have 0 acceleration from this side of the equation is going to equal 88.83 plus 8 alpha dBA cosine 30. So alpha dBA is negative 12.821 radians per second squared. And then for the J direction, I have acceleration of A. It's going to equal 8 times that alpha, which is negative 12.821, times sine of 30. So acceleration of A is negative 51.28 inches per second squared in the J. Alpha was negative 12.821. And then since finding the acceleration in point D is literally the same process, I'm going to go ahead and just put my solution up here and we'll talk about it, but it's literally the same steps. So basically what you would do for acceleration in point D is you would draw your tangential and your normal components relative to B. You'd write out your equation, AD equals AB plus the tangential and plus the normal components. But instead this time, so we know that AD, it's kind of off in space, right? So with point A, we know that it can only move in the J direction. But with D, it could be moving in the I and the J. So we already know what alpha was equal to. And so whenever you solve, you'll literally get an AD is equal to an I and a J component. And so that's all you would do for that one. It's not too bad. These are just tedious. My suggestion for these problems, start with the one that you know the most about. Generally in the problem they'll say, this one has an angular velocity of blank, and it's constant. Solve for this point here. So you basically start with the one that you're given, find the point, then go to like the span of the next one, and then find the point. So you basically go like, so if you're given angular velocity, you would find the translational velocity at the point, and then you know that that's the same on both, so you'd relate it that way. Find the omega, or the angular velocity of whichever one that you didn't know anything about, and then you can find the velocity at the endpoints. You're basically just kind of like inching your way along it. Let's move on to some more fun stuff, unless there's any questions about this thing. Good. Good? Okay. So for this one should be a little interesting because I don't really think your homework touched on this topic too much. So this is for plane motion relative to a rotating frame. So I threw one of these problems on there just so we could get a little practice. I really like this one because this one kind of just helps with the concepts. It's very similar to an example in the book. So it says the collar P slides outward at a constant relative speed u along rod AB, which rotates counterclockwise with a constant angular velocity of 20 RPM. So basically what's happening is this thing, so P starts at 250 millimeters. So it's like at the center of this rod, and then this rod goes from 0 degrees and it rotates up to 90 degrees. And so whenever it rotates upwards, it sends that thing sliding along the surface. Can you guys kind of imagine that? So as it like rotates up, it's gonna the centripetal acceleration is gonna cause it to move along the surface. And it says that the collar reaches B when theta equals 90. So then it says find the magnitude of the acceleration of the collar P just as it reaches B. So we're gonna find whatever that acceleration is that causes it to move from the initial point when it's 0 degrees all the way up to B whenever it's at 90 degrees. Can you guys kind of visualize what's happening for it? Okay. So knowns and unknowns. So we know that it says omega AB is 20 RPM. Multiply that by 2 pi over 60, and we get 2 over 3 pi radians per second. Going that way. It says that it's at a constant angular velocity, so that means that alpha is 0. And then we know that r is equal to 0.25 when theta is 0, and r is equal to 0.5 when theta is 90 degrees. We don't want to work in degrees. We want to work in radians. So this is equal to pi over 2 radians. And you'll see why in a minute. So what we can do is look at rotational motion. So basically, how long does it take that rod to go from horizontal to vertical? So we know its initial angle, we know its final angle, and we know its angular velocity. So we can use this equation. So for rotational motion, we can say that theta is equal to theta naught plus omega t. And we know that alpha is 0. From this, we can say that t is theta minus theta naught divided by omega. So that is pi over 2 minus 0 divided by 2 over 3 pi radians per second, which gives you 0.75 seconds. So that's the time it takes to go from position 1 to position 2. Now there's another thing that we have to look at. So we're also told that, so basically what we did was we looked at rod AB first. So this was for AB. Now what we can do is we can look at P relative to AB. So I'm going to call this motion along AB. And this is just linear motion. Like, this is the stuff that we were doing at the beginning of the semester. So R is equal to R naught plus the velocity, which they said is u. So it moves with the velocity of u along the rod, times the time. So do you see how similar this equation is to this one? Very similar. So we know R, we know R naught, and we just found time, so we can find U. So U is going to equal R minus R naught divided by T. So R is equal to 0.5 minus 0.25 divided by 0.75, which gives you 0.3 repeating meters per second. So we can say that U, or if you look at the textbook, which these equations get really confusing really fast. But do you guys remember this lovely stuff? This is what we're doing right now. So this velocity that we just found is the velocity of point P relative to AB. Or you can just leave it as U, whatever you want to do with it. And now we're getting into the fun stuff with the plane motion. So step 4, plane motion relative to rotating frame. So basically, I thought it was a little confusing how this was explained in class, but the way that I see it is you have a point P, and it's moving along something that's rotating. Leave it at that. The rotating frame, that's what I'm calling AB. So the rod that's rotating, that's our rotating frame, and then you just have something that's moving along it. So don't try to overthink it. And if you think that you'll get too confused by it, try to understand the components in the equation. And I'll show you a diagram that I usually draw with these, and it kind of helps me keep everything clear. So we have to find the magnitude of the acceleration of the color P just as it reaches B. So we're looking at it whenever theta is 90 degrees. So we have point A, and here's point B. And so we know that P has reached point B, so it's up top. And we know that this has our omega, which we know. And now let's just talk about the components that we have. So we know that alpha is 0, right? So do I have a tangential acceleration? No, so I'll draw it on here just so we're clear. So we could say that AT is equal to 0. Let's talk about our normal acceleration. So I'm going to call this AP prime, and that's just to stay consistent with the book. Or you can call it AN, whatever you want to call it. And that's just going to equal what we've done before, which is omega squared r. But then there's one more component of acceleration that we need to talk about. So what do you guys know of Coriolis acceleration? Okay, so here's how I think of Coriolis. There was an example in the book that I looked at, and basically every time I think of it, I relate it back to this. So imagine that you have like a ladybug crawling across like a record player. So the record player is spinning, and the ladybug is crawling across it. The ladybug's going to look like it's moving in a curve, even though to the ladybug, it's moving in a straight line. But to us, looking down, the ladybug looks like it's curving. That's Coriolis acceleration. There's other videos online, and Dr. Nader used to play it in class, and it made everyone feel very motion sick. But basically, there were like two scientists on like a, what do you call those? A teeter-totter. But it was like a teeter-totter that rotated. And so as they were like rotating and spinning around, they were throwing a ball to each other. So to them, it's as if like I'm looking at you and I throw a ball to you. Like to us, it looks like it's moving straight. But because we're rotating, the ball's going to have like a curved path. it's also, Coriolis is also what causes hurricanes to spin. So if you want to look up some interesting, it's actually really interesting. So basically the equation for it, so we're going to have an AC, and it's just going to be 2 omega times u. So it's going to be, you can look at the equation from the book, but Coriolis acceleration, so don't get bogged down by like the capital omegas and everything, just kind of understand what's happening. So it's going to be 2 times the rotational velocity of the frame, which in our case is omega AB, and then you cross it with the velocity of whatever, if it's the ladybug, whatever is moving across the rotating frame. Does that kind of make sense? So putting all this down onto the paper, so we can write this as the acceleration of P is equal to AP prime plus AP relative to AB, I'm just writing it all out, plus 2 omega cross VP relative to AB. So that's the equation that would probably be on your formula sheet. So AP prime, this component, this is your AT plus your AN. But we said that AT was 0, right? So all we have is AN. So we have AP is equal to, we have omega squared R. The AP relative to AB. So that's if point P, or if the collar on AB, if as it were rotating, it were like speeding up as it were going across the surface of it, then we would have an acceleration there. But it says that u, or the velocity that it's moving across that rotating rod, that it's moving with a constant velocity, so the acceleration is 0. Is everyone okay with that? So the AP relative to AB is the acceleration of the collar along that rod. Since it has constant velocity, that's 0. And then we have, sorry, this should be a negative sign there. Then we have plus 2 omega cross VP relative to AB, which is just u, which we found already. So now we just plug everything in. So we have AP is equal to negative omega, which is 2 over 3 pi, and that's squared, times the R. So sorry, I forgot to write that down. So the distance from A to B is going to be 0.5 meters. So this is 0.5. And this is acting in the negative j direction. Then I have plus 2, and then the omega is 2 over 3 pi. And then I have to include the VP relative to AB, which is 0.33. But notice, I already drew it on the diagram, and it's going to the left. You could do the cross product for this and get this sign that way, but this is actually a negative sign there. Because if we do, so if I were to do omega k cross with j, so if I look at my circle, I, j, k, and this is the positive direction. So if I were to say omega cross r, right? That would give me a negative j, because it's going against the circle. Sorry, negative I. And then simplifying this and solving, you get AP is negative 1.396I minus 2.193J, and then writing out the magnitude, we get 2.6 meters per second squared. I don't think, so I feel like if she were to give you a problem on plane motion relative to a rotating frame, I don't think it would be much harder than this one. I think this is a really good problem because it kind of hits all the conceptuals for it. Are there any questions about this topic? Ready to move on to the next one? Okay. So now let's move on to chapter 16. So I feel like in my opinion, chapter 15 is the hardest chapter in the book. I feel like chapters 16 and 17 are pretty straightforward, especially 16. I like how all of my pins were down here, and now I put them all up in my space. So I always tell people that chapter 16 is literally just statics, but instead of everything equals 0, everything equals either MA or I alpha. And then you're just solving for stuff. So this problem says, I think this was a homework problem. Was it? Yeah, I thought so. So it says the flywheel shown has a radius of 20 inches. So I guess I could draw this. I'll draw in here. So we have a radius of 20 inches. A weight, I'll just write it out. So knowns and unknowns. So radius, 20 inches. Weight of the flywheel, I'm going to call it F, is equal to 250 pounds. Radius of gyration, so that's K, is equal to 15 inches. And then we have weight of block A is 30 pounds. So this system is released from rest. So we know that VA naught is equal to 0. Neglect friction. Find the acceleration of block A. And the speed of block A after it has moved 5 feet. So VA after 5 feet. Okay. So just for like some housekeeping stuff, I tried to like simplify everything early on. So we know that if we're given a weight, then that's a force in this class. Like don't try to confuse yourself or think otherwise. So what I did for this problem is I went ahead and converted all my knowns into feet or slugs, which I just wrote as pounds second squared over feet, just to keep it simple. So this radius is 1.67 feet. My radius of gyration is 1.25 feet. Mass of the flywheel. So how would I convert from weight to mass? Good, so we would have 250 divided by 32.2, which would give us 7.764 pounds second squared over feet. And you can do the, oh my gosh, mass of A would be 30 over 32.2, which is 0.9317. Okay. So that's just to keep everything simple. So if you're given radius of gyration, we know that this is chapter 16. We're going to have to find an I value. I is what? What does I stand for? Moment of inertia, good. So if I'm given radius of gyration, what's the equation for moment of inertia? mk squared, good. So we know, so step 2, equations. I is equal to mk squared. If they did not give you k, then you would have to use that chart that she said she would provide, and you would have to use like the radius or the shape of the figure to find it. What? So what else do we know? So we're asked to find the velocity of A after 5 feet. And so we know that we're going to find the acceleration of A. I'm just going to go ahead and write this equation out here. So VA squared is going to equal VA naught squared plus 2 times acceleration of A times delta x. We're going to have to use that equation for the second part. So let's do a free body diagram and kinetic diagram. So for my free body diagram, what forces do I need to include? Good. So for the tension, I'm just going to call that MAG. Because that's all it is. It's just A hanging from that point. What else? Good. So we're going to have the weight of the flywheel. I guess I could just write this as the weight, or I could just write it this way, MFG. I don't know why I changed it up. And then we're also going to have the supports. I heard someone say it. So we have Fx and we have Fy. So that's where the statics is. And then the only thing that's going to change from before is now we're going to have this thing. So this is our I alpha, so it's rotating about the center. It can't translate about that point, but then we can come over here and put this. MA times the acceleration of A. This works. But there's several different ways you can solve this. So now what we do is step 4, your equations of motion. So if we take and do sum of moments about, I'm going to call this point here point F. So if I say sum of moments about point F, I'm going to set this equal to the sum of moments about point F effective. That's literally the same thing as the sum of moments due to, like on your free body or on your kinetic diagram. So let's look at our free body diagram first. So Fx, Fy, and the weight of the flywheel, since those all act about the center, those are all 0. And then I have, let's say that clockwise is positive. So I'm going to have MAG times the radius r, and that's going clockwise, so it's positive, is equal to, what was that? I said that clockwise was positive. Yeah, so you can set whichever one you want, so long as you state it. And then this is going to equal I alpha plus MA AA times R. So now let's just plug and chug. So we have weight of A times R is equal to, I don't know why I did this, but basically we're running a little close to time. We have about 30 minutes left, so I'm just going to show the rest of this one. It's literally just solving the system. So we were at this point here. I simplified this down. I got to this point and just plug everything in. You get the acceleration of A is 5.66 going down. And after that, you just plug it into your kinematic equation to get the velocity of A after 5 feet. Any questions about this one? This one's pretty straightforward, I feel like. The next one's a little more difficult.
What do we got?
3, I believe. Yeah, I don't know if we'll be able to get through all of them. But again, my solutions are posted, or they will be. Okay, so let's move on to this thing here. See, I wanted to spend more time on chapter 15 because that's the harder one. So this says a 12-pound uniform plate rotates about A in a vertical plane under the combined effects of gravity and of the vertical force P. Knowing that at the instant shown, the plate has an angular velocity of 20 radians per second and an angular acceleration of 30 radians per second, both counterclockwise. Find the force P, find the components of reaction. So as soon as you see a problem say, find the components of reaction, I really hope that you guys think, oh, I have to use chapter 16 material. So free body diagram, kinetic diagram. After that, your equations of motion, solve the system. Okay, so we'll go ahead and jump into the free body diagram and kinetic diagram. I left out writing out my knowns and unknowns in my equations. So there's my free body diagram. And there's my kinetic diagram. So for my free body diagram, so we said that it's rotating about A. So A is located here. So we're going to have the components of reaction at A. So I have AY, I almost put AX, and then I have AX. I also have the force P, that's pulling it up. And then I have the weight of the plate, and that's at its center. And then just to clarify, this is 5 inches, 5 inches, 4 inches, and then we know that the total, oh, I pointed to the wrong one. We know that that's 20, so the distance from this edge here to the center would be 10. We also know that the distance from A to P, 16. Whatever you want to write out, it doesn't hurt. Now for our kinetic diagram. So here I have point A, but here I have my center, point G. So this thing we're going to say we have our I alpha about point G. But it's not rotating about point G, right? It's rotating about A. So what I can do is say that at point G, I have MAT and I have MAN. It works. So it doesn't matter which way you decide to do it. If you want to do the analysis about point A, you can. You would just have to take into account the fact that I wouldn't be about its center. So the equations that they give you in the chart, they give you the moment of inertia about the centroid of the figure usually. So that's why I picked this way, so that I didn't have to do anything with that equation. Is everyone okay? Okay. So let's write out the next part. So I didn't write this down, but for a rectangular shape, you can get this from the table. I is equal to 1 over 12 m times b squared plus w squared. So this isn't a slender rod. For a slender rod, you would just have like 1 over 12 ml squared, I believe. So this one you have to take into account that it has a thickness to it. So now let's do our equations of motion. So if I take the sum of moments about point A, so that's just me writing my equation out. I'm going to say that counterclockwise is positive. I change them up, but I always try to make sure I indicate which one I choose. So about point A, so I'm going to have P times, what's that distance going to be? That is, so from P to A is 16, but that's 16 inches. I want this in feet, so I have 16 over 12. And then I have W, so P is going counterclockwise, so it's positive. Then for W, it's going clockwise, so we know it's negative. So I have W times 6 over 12, because it's 10 minus 4. And then we set this equal to our kinetic diagram. So we're going to have, so MAN is going towards A, so it's 0. Then we have MAT times 6 over 12. And that is positive. And then we have plus I alpha. So we know AT is the same thing as R alpha, right? So this thing is rotating about point A. So if it's rotating about point A, it's just going to equal R alpha. And that R is the same 6 over 12 that we have here. So we can solve for, we're trying to find the force P and the reactions AX and AY. So from this equation, we can get the force P. So I have P times 16 over 12 minus W times 6 over 12 equal to M alpha times 6 over 12 squared plus, let me plug in the equation for I alpha. I have 1 over 12 M. So my base for this, it doesn't matter which one we pick. I'm going to pick 10 for the base and then 20 for the width. And that's times alpha. And we're told in the problem that it has the angular acceleration of 30 radians per second. So we know alpha. So going through this equation, we know that W is 12 pounds. We know that the mass is just going to be 12 over 32.2. Alpha is 30. This is 12 over 32.2. That's 30. So we have everything except for P. If you solve for P, you should get 9.0225 pounds. Everyone okay? So then what we do next is our sum of forces in X equals sum of forces in X effective. So if I look at my free body diagram, I have AX. If I look at my kinetic diagram, I have MAN. But if I say that to the right is my positive, then this is going to equal negative MAN. So we know that AN is equal to R omega squared. So plugging everything in, so we have AX equals negative 12 over 32.2 times, what was our omega? 20. So we have 20 radians per second squared, and then the R that we have is this distance, which we said was 6 over 12. So AX should be negative 74.534 pounds. And then to find AY, it's the same process. Sum of forces in Y equals sum of forces in Y effective. I'm going to say that up is positive. So we have AY minus W plus P is equal to MAT. So AY is going to equal 12 over 32.2, so that's our M, times AT, which we said is R alpha. So is this the same as before? So 6 over 12 times alpha, which we said was 30, plus the weight, if I move it to the other side, which is 12 pounds, and then minus P, so minus 9.0225. So AY should give you 8.568 pounds. Any questions about that one? Basically, for these problems, draw your free body diagram, draw your kinetic diagram, equations of motion, solve. Be very careful with your signs for it. So that's why I always recommend, whenever you're solving for your EOM, draw which direction you're saying is positive. Any questions? Okay. So we have 20 minutes left, and we got 2 more problems. So we'll at least be able to talk about them. We should be able to get through them. Actually, maybe not. I turned the page. I saw what was next. So we finished chapter 16. For chapter 17, it's plane motion of rigid bodies, so energy and momentum. It's pretty much the same stuff that you learned from chapter 13 earlier this semester, but chapter 13 dealt with particles. Now we're dealing with rigid bodies. It's very similar structurally, but also take note from these solutions that you guys don't have to worry about impact. That's just remnants from a past semester. So she didn't get that far. So let's talk about this thing. I want to say that she did something very similar in class, from what I remember. It feels like it's been a while, though. So we have a slender rod, or a slender 9-pound rod, can rotate in a vertical plane about a pivot at B. A spring of constant 30 pounds per feet and of unstretched length 6 inches is attached to the rod as shown. Knowing that the rod is released from rest in the position shown, find its angular velocity after it's rotated 90 degrees. So for this problem, I see here, so we know that it says that it's in a vertical plane. So the vertical plane means that we have to take the mass and the energy due to gravity into account. We also have a spring here. So I would recommend using conservation of energy for this problem. So I'm not going to write out all my knowns and unknowns, unless you guys want me to. It's up to you. Do you want me to write out all the knowns and unknowns? Yeah, okay. So knowns, unknowns. So we know that the weight is 9 pounds. We know that K, or the spring constant, is 30 pounds per feet. So I'm going to kind of blow your minds here. I'm going to convert this to pounds per inches, which is a little weird, but everything else is in inches, and I just don't feel like converting all that stuff. I'm just going to convert this. So this gives me 2.5 pounds per inch. I know that the spring has an unstretched length of 6 inches. I know that so I can find from here, the mass of this is going to equal 9. So here's where this gets a little strange. We have 9 pounds here, right? And I'm going to divide that by 32.2 feet per second squared, right? So if I'm converting everything to inches instead of feet, I have to convert my mass to a really weird unit. I think I warned you guys in SI that I did a problem like this, and I got lazy, so then I just converted everything weird. Didn't I say that? Never mind. So I get a mass of 0.0233 pounds second squared per inch. So I promise you guys, if you were to do this problem the normal way and get everything in terms of feet rather than inches, you should get the same final answer. But this is just proving kind of a point that, like, so long as you're consistent with your units, it doesn't matter. And we're told to find omega after 90 degrees. And we're going to use, I'm also going to put, and equations. So our equation, T1 plus V1 equals T2 plus V2. All right. Let's draw some diagrams to figure out what is happening here. So in position 1, oh man, my back is starting to hurt from this. So for position 1, so I'm going to draw my initial. The rod is vertical, and I'm just going to draw the forces that I have. So at the center at G, I have my weight on it. Here's point B, and it's in line with point D. And then from here, this is where my spring is attached. So I know from the drawing here that the distance between B and D, so I'm going to redraw this as a different triangle. So the distance between B and D is 14. And then the distance from B to C is 5. And so basically, we know that we're going to have to figure out the stretch of this spring. So that's what I'm doing here, is figuring out how far it's stretched. So I need this, I'm going to call this x. So x squared is going to equal the square root of 14 squared plus 5 squared. So x, oops, I didn't mean to put that. So x is equal to the square root of all that. You get 14.866 inches. Okay, and then I'm actually going to call the line right here, I'm going to call this my datum line, just to keep it simple. So initially, it says that it's released from rest. So what does that mean about my kinetic energy? 0, good. So T1 is 0. Then for potential energy, what kind of potentials do I have to work with for this problem? Elastic and gravity, good. So I'm going to have V1E, V1G. So for elastic potential, the equation is 1/2 K delta X squared. And then for gravity, it's just going to equal mgh or wh. So we can go ahead and solve for these. So we have 1/2 times RK, which we said was 2.5, times our delta X, which is 14.866. So that's the length of our spring that we calculated, minus the unstretched length squared. I didn't give myself enough space. And then for the gravity, it'll be 9 times 7. So we should get V1E is 98.259 pounds per inch. And V1G is going to equal 63 pounds times inch. So that's for our initial. And I'm going to draw this line straight down the middle of my page. So now we're going to look at final. So for the final position, it says it's rotated through 90 degrees. So basically what we're going to have, and it's rotating about point B. So there's my point B. here's my spring, which is attached to C and D. And then my weight is still applied there. I'm basically combining chapter 17 methods with like chapter, I don't know, I'm like doing a bunch of things at once. I put the weight there. I don't even think we need it for this side. And so we said that initially the thing was at rest, but then on this side, we know we're going to have an omega and a velocity at that point, right? So if it were rotating about the centroid, we would just have an omega. But it's rotating about a point B. So we're going to have the tangential component of velocity plus the rotational. Like, we have to look at both sides, or both parts of it. So the distance from from G to B is 7 inches. And I got that because the rod AC, oh, you don't see what I'm pointing at. The rod AC is 24 inches. So that means G is going to be at the center, which is 12 inches. So then the distance from G to B is going to equal 12 minus 5, so 7. So we know from before that the distance from B to D is 14 inches. So how are we going to calculate x for this side?
C is 5 inches.
Good. So x will equal 14 minus 5. So we should get 9 inches for the stretch. And now we're just going to do the same thing. Oh, I forgot to write these out. So for a rod, the I equation is 1 over 12 ml squared. And then as I was saying before, the V bar that I wrote here is just going to equal R omega. So let's look at, let me label these a little better. Kinetic potential. So now let's talk about kinetic for the final case. So what is our equation for kinetic energy for rigid bodies? Before, whenever we talked about this stuff, it was 1/2 mv squared. How do I relate the rotational component into the equation? T2 is equal to 1/2 I omega squared plus 1/2 m v bar squared. You just add it in there. So then, solving for this, we have 1/2 times our I, which is 1 over 12, times the mass, times the length squared, times omega squared, plus 1/2 m v bar squared. So for v bar, I'm going to plug in R omega. And keep in mind that means both components would be squared. So I can say that T2 is going to equal, this is getting pretty messy. I'm going to pull m omega squared out of both sides of this. So if I look at this now, so for this part, I have 1 over 24 L squared. And then on this side, I have plus 1/2. I pulled out the m and the omega squared, so that just leaves me with the r squared. So it simplifies to that. And now plugging in our values, we get T2 is, so we don't know omega. We're trying to find omega. So we still have this unknown sitting here. Our mass is 0.0233, 1/24. Our length is 24 inches. So keep in mind that I solved everything in terms of inches. You could also do it in feet. And then 1/2 times, so this is this distance here. So it's the distance from the center where we're applying all the rotations to the point where it's actually rotating. If that was a sneeze, then bless you.
Bless you.
Oh, okay. So then T2 is 1.1297 omega squared. And then for the potential, so this is nice the way that I set this up. The entire thing is on our datum line now. So that means that the potential due to gravity is 0. So then we just have the elastic potential to worry about. So I can say V1E is 1/2 K delta x squared. So plugging all this in, we have 1/2 times 2.5, and then our delta x will be 9 minus 6 squared. So V1E is 11.25, and our units should be pound, inches. Our units for our kinetic should be pound, second squared inch, all this weird stuff. But now we can apply, so we're getting close to time. Now if we apply conservation of energy, we set our initial equal to our final. So we have 0 plus 98.259 plus 63 is equal to 1.1297 omega squared plus 11.25. So solving for omega, you should end up getting an equation or something that looked like this. Omega squared is 132.791 radians per second squared. So take the square root, take the positive value. Omega is 11.524 radians per second. So the reason this worked the weird way that I did it by using inches is because we were trying to find omega, and the units of omega are radians per second. So there is no, radian is kind of like a distance placeholder, so to speak. It's kind of like whenever you multiply something by 1. Are we okay with this one? Yeah, I know it's tedious. So the last problem, I know we didn't have time to get to. I will put it up here just so we can kind of talk about it really fast. So for this problem, it says, if I pull it down a little further, 45-pound cylindrical roller initially at rest is acted upon by the 20-pound force shown. Knowing that the body rolls without slipping, find the velocity of its center after it's moved 5 feet and the friction force required to prevent slipping. So, like, generally speaking, you're going to draw some sort of diagram for any of these problems. It's only to help you. It's not to, like, hurt you. And if she does give good partial credit, I would say that having a good free body diagram would be means for more partial credit, because it shows that you understand what's going on with the problem. So for this one, free body diagram, kinetic diagram, all of your forces. Friction always opposes the direction of motion, so it's going to the left. For the kinetic diagram, we have the I alpha and the MA. So for this one, I used work energy so that I could find the V, because the reason I did this way is because it says find the velocity after it's moved a certain distance. So because of that, I wanted to see, like, the work due to it. So initially, kinetic is 0. Final, we have that equation that we looked at before. The work that we're talking about is due to the force that's pulling it. So we have the F delta X, and F is 20 pounds. So then you literally just set that equation up, solve for the V bar. It's pretty straightforward, I feel like. And then from the kinematics equation, so you know V squared equals V naught squared plus 2A delta X, you can find the acceleration that it's moving at. And then once you know that acceleration, you can use the chapter 16 material. So you can do sum of forces in X from your free body diagram. You would have the force that's pulling it minus the force of friction is equal to MA. Solve for the force of friction. I think they're pretty straightforward. So we're pretty much close to time. I did want to make an announcement. Hiring for SI, so if you want to do my job in the spring, hiring is still open. And I promise you guys, it's a really fun job. It's 10 hours a week. It's scheduled around your classes. So basically you can go from class to like hold an SI session, which is work, then back to class. You also get paid to attend the lectures. So you get to refresh on all of this material, which is very useful in your future classes. I think it's a really great job. I've been there for 4 years, but this is my last semester doing it, so someone needs to replace me. And no one has applied yet, so someone needs to apply, because I can't do this forever. So good luck on your final. I'm sure all of you will do great. If you have any questions, I'll stick around for a few minutes and I can answer some.